OK, we have no time to waste, so definition. This talk is going to be a bit heavy on equations and light on everything else. And of course, I wouldn't contemplate sneaking an actual algorithm past this audience. So it's all lower bounds. So the notion I'm interested in is this notion of local indistinguishability of distributions. So you have two distributions over. In this talk, they will be over bits, but you can also think them of being over sort of larger alphabet symbols. And what we want to study is this sort of the property that we want from this distribution is that if we look at them locally, they're distributions over n bits. But if you look at any k of those bits, you see the same thing in both distributions. So you might have heard of sort of local independence. And so that talks about one distribution being locally indistinguishable from uniform. But this is a definition that says that two distributions should be indistinguishable from one another. And sort of there is a canonical example that, when I teach my students in probability, I have to spend hours convincing them that this is real. But for you, you know what it is, right? So I take 3 bits, and then if I condition on their XOR being 0 or 1, no 2 bits of the 3 will give me any information, but all 3 together are very different from one another. So I'll just sort of, it's really all equations. I'm just going to try to give you why one might be interested in this. And actually, I was convinced by Yuval that this is an interesting notion. And the reason that it is interesting is because, when you define multi-party computation and secret sharing, this is the definition you use, right? You have a bunch of parties, and then any local view on a subset of the parties should be the same, regardless of sort of what is going on. But globally, something has to happen, right? So kind of questions about sort of what you can do with multi-party computation, but also about security of multi-party computation, whether sort of having this local notion of security gives you some global security, which, again, Yuval convinced me is something that is interesting, can be formulated in this language as well. So this is sort of one reason why you might want to study. I think another reason is that it's an interesting notion of security by itself. And it's an interesting notion when you talk about security against real adversaries. And what I mean by real is not real as to what the real cryptographers do, but by real, I mean real numbers, as opposed to finite fields. OK? So I'll give you sort of my high-level view picture of algorithms, which is probably very inaccurate. But in my understanding, there are 2 algorithms, right? There is gradient descent, and there is Gaussian elimination. And if you can handle those 2, then you're secure. OK? So gradient descent and all these kinds of algorithms, I don't know, semi-definite programming, hierarchies, blah, 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 they work with real numbers. And actually, a lot of those algorithms, when you formalize sort of as what they can and they cannot do, when you want to say, well, this algorithm cannot solve this problem, what do you say? Well, you give 2 distributions which are locally indistinguishable, but globally look very different. And that's how you prove security. So as long as you have this local property, you kind of get automatically secure against sort of all the things that your machine learning people tell you, oh, we can do this. No, you cannot do it because it's locally indistinguishable. OK, so I think that's sort of another reason why, if you can handle 50% of the algorithms, then you're 50% secure. You're already in pretty good shape. OK, so what's special? Why symmetric distributions? This talk is about symmetric distribution. Well, I can tell you about how symmetric distributions are a very important class of distribution and blah, blah, blah. But the real reason why I want to talk about symmetric distribution is because I can do this cool demo. OK, so look at this very carefully. Look at it again. Look again. And look again. OK? Do you see the picture? Kind of. OK. So what happened here? Well, this is an example. This is an old example. It's an example that was sort of an idea that was suggested by Naur and Shamir in like the early 90s. And it's called visual cryptography, right? So you give these transparencies to people. They're the shares, right? And then when each one of them, they look at what they have. They have no information. 2 of them come together. They look at their things. They have no information. But when they come together and superimpose them, they kind of get the picture, right? There is some speckles and stuff, but you can see what's going on here, right? You can recover the picture. And this is an example of a secret sharing scheme. So what kind of secret sharing scheme is this? Well, it works at the bit level. So the way that this is implemented is that you sort of pixelate the image, and you do something to every pixel separately. So let's start by looking at what happens when you reconstruct. you superimpose the transparencies, so transparent bits stay transparent, and if you have at least one colored bit, then you get a colored image. So it's a secret sharing scheme where the secret is a 0 or a 1. The shares are zeros or ones. But then we have this kind of weird constraint that the way that you reconstruct them is not by sort of XORing or doing linear algebra or the other kinds of things that you're used to doing, but you actually apply the end function to the shares, right? Because like putting transparencies together is exactly applying the end function on the underlying bits. And sort of for the last 4 or 5 years, I have been trying to figure out like how this works and why it works, okay? And so I will tell you the story. It has some twists, so let me sort of, this is my first part of the talk, is I'm going to try to explain to you how do you actually do this? How do you implement these visual schemes? Okay, so this is where the connection that you've all hinted at with approximating polynomials comes in. And so the way that we're going to think about it is we're not going to worry about sort of right now how the sharing works, but we're actually going to try to think about the security. What does it mean that this thing is secure? That when you look at one or you look at any pair of them, you cannot tell apart the two shares. So you have these bit sequences, right? These are the shares of a single bit. The x's are shares of zeros. The y's are shares of 1. And instead of thinking of the bits themselves, we're going to think about their probability mass functions. So sort of, if I want to share a 0, I assign some probability to each kind of sequence of shares. If I want to share a 1, I assign a different probability. So there are these two different probability distributions. And the trick is to look at the difference of the probability mass function. So this is just, I can think of it as a real valued function. Sometimes it takes positive values when I share a 0. Sometimes it takes negative values when I share a 1. And the nice thing about this representation is that local security has a very kind of compact encoding in this formula. And what local security means is that this function is actually orthogonal to all low-degree polynomials. Okay? So you can think of a distinguisher as being some kind of, if I sort of look at k positions, a window of k positions, I can think of this as being some kind of local function or a monomial. And then if I take linear combinations of monomials, this will not help me distinguish between these two distributions. So I can sort of formulate the indistinguishability in this algebraic way. I can say sort of this difference between the two distributions is orthogonal to all low-degree polynomials. On the other hand, I want to be able to distinguish these two distributions by the end function. So what does this mean? This means that there is some kind of global thing going on here. And the global thing is that the difference of distribution actually has to have very large correlation with the end function itself. 1/2 happens to be the maximum correlation that it can have for a 0, 1 function. And it says that sort of it is close to 1/2. So like the distributions align with the end function. Yes?
Just going back to the local thing.
Yes.
If I wanted to be like a sufficient condition to guarantee k-wise indistinguishability, then should I range over all polynomials, or is it suffices to go over all monomials?
It suffices to go over all monomials, so it's an equivalent formulation. So you're right that in some sense this is a...
Just monomials, right?
Yeah, it's a stronger formulation, but it's going to be more convenient to do it in this way. Yes?
Does it have to be 0 or just something very, very small?
If you want, okay, so here I'm aiming for perfect security. We're going to go to sort of statistical security later on. But if I want perfect security, it has to be exactly 0 for all the polynomials. Yeah, good questions. So actually, you can ask this kind of sort of, you can formulate any kind of secret sharing scheme when you have over bits, when you have the reconstruction function fixed in this way. So here it's the special case when it's the end function. And this is what the properties that it has to satisfy, right? It means that, that you have to be orthogonal to low-degree polynomial, but you have to have high correlation with the reconstruction function. Okay, so one way to sort of understand what's going on is to ask sort of not when you can do it, but when you cannot do it. So when are these two conditions kind of in contradiction to one another? Yes? So k is n, let's say k is smaller. K is like n over 2 or square root of n here. But for which function, so I'm thinking about f now, like the function f, the one that I used to do the reconstruction. Which functions cannot reconstruct? If I'm a local function itself, I can certainly not reconstruct, right? Because I only see a subset of the shares. But in general, if I'm a low-degree polynomial, then these two functions are in contradiction to one another. So a low-degree polynomial cannot reconstruct from the shares. Actually, it's not, it's not necessary to be a low-degree polynomial. As long as I'm close to a low-degree polynomial in the approximate sense, then I can also not tell, sort of this is related to what Prashant was saying, I cannot kind of tell these two conditions very well apart, right? So this is exactly this notion of approximate degree, which comes from complexity theory, and which is formulated like this. So this is the right way to say it, that the function, the reconstruction function, cannot be approximated by a low-degree polynomial pointwise. So there must be at least some point where the difference between the value of the function and the value of the polynomial has to be large, more than epsilon, more than this reconstruction advantage that I have. Okay? So this is sort of, we ask the opposite question, when is it that you cannot reconstruct? And this is sort of how it works out with the parameters. So if f can distinguish between the two distributions, it must be that the function has high approximate degree, that it cannot be, yes?
Why do you care about worst case approximation? It matter if it's like the distance is far?
Essentially, it's because you have no control over these two distributions, right? Maybe they put their weight on a single point, right? So that's why this notion comes out. Okay? And it turns out it's equivalent. It's an if and only if in the Boolean case, when the values are bits. And this is, the reason it's an if and only if is because of LP duality. So I showed you sort of the weak duality part of the proof, but then it turns out that there is strong duality, that sort of the approximate degree formulation is the dual of this secret sharing, and then strong duality tells you that these are the same notion, right? So what does it say is that proofs of approximate degree lower bounds are secret sharing schemes. Okay? So if I want to share, all I have to figure out is how the proof works. Okay? So what about the n function? Well, this was the first function that was studied for approximate degree. Okay? How do I approximate, or how do I prove to you that the n function cannot be approximated by a low degree polynomial? Okay, so let's see how the n function can be approximated by a low degree polynomial. Well, the n function is very symmetric. It's 0 everywhere and then 1 somewhere. So let's sort of try univariate polynomials first, right? And then we symmetrize them in some way. So let's start with x to the d, right? This is a degree d polynomial, and I want to approximate this function, which is 0 everywhere, and then it jumps to 1 as quickly as possible, right? So these are strings of Hamming weight 0, 1, 2, 3, and so on. Is this the best I can do? It turns out it's not. There is this Chebyshev polynomial, which is much better, which sort of, it wiggles around a little bit here, but then it jumps really fast. Okay, so if I sort of think of this as a function of the Hamming weights, right, I can kind of pack in a lot more Hamming weights here and then do the jump. And this actually gives you a very good approximation of the n function. It has degree, so the jump here, sort of the derivative is roughly d squared, so it allows you to approximate an n function of n bit by a polynomial of degree square root of n, right? And Nissan and Segedi show that this is tight, that this is the best you can do, okay? And so, okay, so they have a proof that, that the approximate degree of the n function is large, and this proof should give you a secret sharing scheme. So for like the last 4 or 5 years, I have been trying to understand what are these two distributions. So you look at their proof, and how do they do their proof? Well, the way they do their proof is they kind of work backwards. They say, well, I'm going to kind of argue that this is the best polynomial I can use for the approximation. And then it's really nasty, because you're actually approximating functions over numbers, over bits, but this is something that works over reals. So you have to use this theorem from analysis. You have to convert the numbers into bits. I couldn't figure out what are the distributions. And other people have tried to do it. You can write down some formulas, but they look really nasty. Okay? So the first thing I want to show you is a new proof of their result. Okay? So I will show you what these two distributions are. And actually, they're not sort of super intuitive in the sense that this is the first secret sharing scheme you would come up with, but at least I can put them on one slide. I can write down the formula on one slide. So let me explain to you sort of how the formula works. There is this one element I'm going to pull out of the hat. I don't quite understand where it comes from, but after that, you'll see. Like everything is like, the proof will be very easy. So I'm going to define this function. It's a function over the Boolean cube. I'm going to represent the inputs as -1 and 1. And the thing to notice, it's a non-negative function, so it assigns a non-negative number to each point of the Boolean cube. And the number is, first I'm going to sample a subset of bits from some distribution I will describe you in a minute. And then I'm going to average out the parity over this subset. And I'm going to square the value. Okay? So it's some kind of function I pull out of the hat. It assigns a real number to every point of the Boolean cube. How do I sample this subset? This subset is going to be a uniformly random subset from the lower part of the cube. So I'm going to look at all strings of Hamming weight less than n minus square root of n over 2. So it's going to be a little bit below the middle part of the cube. And then I can write down this function. So that's the definition. Okay? Is it clear what it is? It's well defined. It's not clear why it's meaningful. But now that I have this definition, I can tell you what the secret sharing scheme is. It's extremely simple. To share a bit b, I sample x with probability proportional to this number, condition on the parity being the bit. So if the parity is, so for parity 0 string, I sample from sort of the even Hamming weights with this kind of probability. For parity 1 string, I sample from the odd Hamming weights with this probability. Okay? So these are the two distributions. This is how I do. This is how I share. This is how I share visually. Okay. So here is the security proof. This is the first thing I want to show you. So what do I need to do to argue security? First, I need to argue that the difference between these two distributions, when I write down the probability mass functions, is perpendicular to all low-degree polynomials. And the second thing is that I have high correlation with the end function. Why is it orthogonal to all low-degree polynomials? Okay. So this is the difference between these two probability distributions. These are the weights. Sort of the parity tells me whether I take a plus sign or a minus sign, and then I have to normalize by some unknown factor z, which we'll talk about later. Okay? So this is the difference. You stare at this formula, and you notice this is a polynomial that doesn't have any low-degree terms. Why? This is a low-degree polynomial because we only took things from the lower part of the cube. And then when I multiply it by the parity, sort of all the low-degree terms become high-degree terms. So everything vanishes. Right? So that's the whole proof of security. Right? Now, the only thing I have to prove is that I can reconstruct. So what does it mean I have to reconstruct? It means that when I take the end of the bits, I can distinguish between these two distributions. Okay? So actually, I'm going to cheat a little bit. I'm not going to take the end. I'm going to take the NOR, I guess. So I'm going to sort of, so my distinguisher is the point function, something that sort of only evaluates to 1 when all the inputs are 1, and it evaluates to 0 everywhere else. Okay? And what is the probability that it distinguishes between these two distributions? Well, this takes value 1, so it's exactly 1 over the normalization constant. Right? So as long as this probability here is small, as long as this normalization constant here is small, I can distinguish between these two distributions very easily. Okay? So that's all you have to do. All you have to do is figure out sort of what this normalization is. And sort of, if you know Fourier analysis, this is like a two-line proof in Fourier analysis. If you don't know Fourier analysis, I'm going to do the two-line proof in Fourier analysis for you. Okay? So you have to evaluate this expression. What is this expression? I'm taking the average of a parity over subsets of the cube, and then I'm summing these weights over the whole cube. So when you see an expression like this, there is only one thing you can do. And I mean, sometimes it doesn't work, but when it works miraculously. And the trick is that you rewrite the square of an expectation as a product of expectations over independent sets. So that's sort of the trick in Fourier analysis that works most of the time. Okay? And the reason that it's nice is that when these two things are independent, then you can multiply the probabilities inside the expectations themselves. And now we have a product of parity functions over different sets, which is the parity over the symmetric difference. You switch the expectation and the summation, and now we have this very nice expression, which is the sum of a parity over some set over all the points in the cube. Well, parity is a periodic function, so unless the set is empty, it vanishes completely. Right? So what you get here is something that evaluates to 0 when the sets are different, and it evaluates to 1 when the sets are the same. So it evaluates to 2 to the n with the probability that these two sets are the same, which is 1 over the total number of sets in this lower part of the cube that I'm picking from. Okay? So that's the whole calculation. It's an identity. There are no inequalities there. And it just works out.
That's the reason why you took the squared on top. Why do you find the squared and not
Yes. Yes.
The privacy would work even if it's not.
the privacy would work even if it's linear, but this calculation, I don't know if it would work if it was linear. Yeah. Also, you need it to be positive, so you need to do something to make it positive, right? Okay. So this is just 1 over the probability, right? It's the inverse of the number of the measure of this part of the cube divided by 2 to the n, like the measure of this whole part of the cube. So, and sort of this is sort of the other reason, right? There are 2 balancing things here. There is the other reason why I picked something that has strings of weight less than n over square root of n, because then the measure of this set is going to be a constant measure, and then I recover with probability, which is very large, right? That I can distinguish the 2 distributions easily. And sort of when you put the whole thing together, I'm not going to do the precise calculation, you actually get a pretty nice formula about what happens here, and it says that you can actually, for any parameter k, you can get k-secure visual secret sharing with this reconstruction advantage, right? So this is twice the probability of the measure of this set, of this collection of sets, okay? And actually, this gives you the right number when k is large. So it's asymptotically accurate when k is large. So if I want security against many parties, then the reconstruction advantage cannot be very large, but this gives you pretty much the best thing you can do. When k is small, it's not the right expression. This is what it gives you. This is kind of the more interesting setting of parameters for crypto, maybe, because that's when the reconstruction advantage is high. This gives you 1 minus k divided by square root of n. It turns out the right answer that you can get by sort of through the Nissan-Szegedi proof with massaging it is k squared over n. So there is something there that possibly says that this method is not right in that range of parameter and can be further improved. Okay? Okay. How am I doing on time? I started late, so.
Yeah, you have 21 minutes.
21 minutes. Okay. I want to do a lot in those 21 minutes, so let me sort of do very quickly tell you about sort of one it's an open question, and it's also like a potential application of this method. So sort of what this shows, sort of now, the cryptographers are interested in secret sharing, complexity theorists are interested in approximate degree. So now can we turn this around, and can we use this method to say something about approximate degree? And what it says directly is something that has been known since 1991, which is that the approximate degree of the n function is square root of n. Okay? So let me tell you about sort of one question that has been open for a long time, which is sort of one of the reasons why approximate degree is interesting in complexity theory is that it provides lower bounds for quantum algorithms. Okay, it provides query complexity lower bounds for quantum algorithms. So if you want to prove upper bounds, then there was this work about, I don't know, 10, 15 years ago where people said, well, the n function, it actually models what happens when you search when you do quantum search in a database, but maybe you want to compute some kind of other functionalities on the quantum database, right? So one question that they ask is what happens when the functionality you want to compute is a read-once formula? And Ben Reichard gave this algorithm that showed that every read-once formula with AND and OR gate has sort of the Grover speedup. So it has a quantum algorithm with complexity square root of the database side. And sort of he proved that this is optimal for quantum algorithms, but the proof method that he used was not via the connection to approximate degree. So one open question, I don't know if I should call it a conjecture because I've never actually seen it conjecture, but I think it has been kind of looked at by many people, is whether there is a matching lower bound, right? And the reason I put this for all quantifier here is that this is something that refers to any specific read-once formula. Is it true that for any specific read-once formula, the approximate degree is exactly square root of n, square root of the number of variables? Okay, so there is kind of a lot of evidence that this should be true, but it's not known. So one possible way of going about proving it, and sort of, I want to kind of convince you that this is also a natural conjecture sort of viewed from the crypto perspective and tell you sort of why it's natural, but it's not trivial. Okay? So one sort of natural way to look at it is that when you take a read-once formula, what's a read-once formula? It's an AND, and then you do some ORs, and then you do some ANDs, and then you do some ORs, and so on. These are built by composition, right? So I take something on the top, and I compose it with the same structure at the bottom. So composition is something that in crypto we do all the time, right? So in particular, lower bounds on approximate degree for formula or for composed functions are precisely compositions of secret sharing schemes in the secret sharing language. So sort of one thing you can ask is whether, the approximate degree of a composed function of this form, I take f and I evaluate it on many copies of g of independent bits, does it have to be larger than the product of the degrees? And the reason that sort of you might believe this is that when you formulate it as a secret sharing question, what this says is that if I have a secret sharing scheme where f can reconstruct, and I have a secret sharing scheme where g can reconstruct, then I get one where this whole function can reconstruct, where the security is sort of the product of the two. So if this is secure against m parties and this is secure against n parties, then the security would be m times n, or something like that, right? And you can say, well, it's clear what to do, right? I take a bit here, I share it under f, then I get these shares, I share each one of them under g, and I get the shares at the bottom. So why is this not a proof of the conjecture? Like, why doesn't it automatically give us lower bounds on approximate degree? Any guesses? Well, it's the speckles that showed up when you shared the image, right? When you do secret sharing, then it doesn't reconstruct perfectly, but you know there was this noise in the image, and that's inherent, right? So when you do the composition, the noise kind of goes out of control. You have noise here, you share noisy bits, you have no idea what's going to happen when you try to do the reconstruction in the other direction. And that's the reason why this conjecture is apparently hard to prove, right? But it sounds very natural. Okay. So one thing that sort of one can try to do is try to prove special cases on the conjecture. So you can ask sort of what happens if I take an n and I compose it at or at depth 2. Okay? And Sherstov sort of did this. So in that case, you can analyze it because it turns out that if you do things right, the noise is not a problem. And he showed that if I take a balanced read once formula with an OR gate and AND gates that have the same fan-in at the bottom, then you can prove the conjecture. The degree is square root of n. But he couldn't do it for the unbalanced case. And then Prashant here and Pritish, right? Pritish Kamat, I found this thing on the internet. They did a class project when they were at MIT. And they said, you know what? They didn't write it in this language, but in secret sharing language. Essentially what they did is, you can do this. All you have to do is, instead of designing a secret sharing scheme for sort of threshold access structure, right? Where you know, like all parties, like if you have under a certain number cannot reconstruct and all of them can reconstruct, you do something for different access structure. And the access structure that you need to do in order to handle unbalanced formula turns out to be weighted threshold. Okay? So each party gets a weight, and only when the total weight exceeds a certain number should you be allowed to reconstruct. And the question is, can you design such a scheme? And in fact, the proof that I gave you extends to that case. So instead of taking this set S to be from the lower part of the cube, I do some kind of weighted threshold. And you get sort of what is required for the proof to go through. So you can actually prove using this that the approximate degree of the read once 2 formula is square root of n. So I was very excited when I discovered this. But then it turned out that there is sort of using quantum methods, people prove something that's even more general, that only works not only for degree 2, but it works for sort of depth D formula. And it has been shown by Ben David and his co-authors, I don't remember, that for read once formulas of depth D, the approximate degree is as large as 2 to the minus D times square root of n. Okay, so that's the first part of my talk. And now I want to tell you sort of a bit more. I'll see how far I can get. And the second question I want to address, which is something that sort of I think is interesting because it kind of uses this connection, but it's a purely cryptographic question. It doesn't really, I don't know sort of an analogous statement about polynomials, is the question of statistical security. Okay? So if you look at what happened in the demo that I did, right? We did this share. We share this image among n parties. If all n get together, they can reconstruct the image with some large advantage, like, I don't know, 90%. If fewer than square roots of n parties come together, they get no advantage whatsoever. Security is perfect. We don't reveal any information about the image. What happens in the middle? Okay? So does it go from square root of n like very fast to n? Does it rise slowly? And so this is the second kind of thing that we can prove. And again, it's a more general statement. It says that if I take not only the shares of 0 and 1, if I take any two symmetric distributions that are locally indistinguishable, sort of they're perfectly indistinguishable up to k bits. Now I go past k, I go at k plus 1, k plus 2. The distinguishing advantage goes like this. it means that roughly, if I have big k bits instead of little k bits, so now I give a distinguisher a much bigger window, then the advantage goes exponentially in little k squared over big K. So in particular, say, if I do visual secret sharing, little k is square root of n, so it goes down as exponential in n over big K. So the more parties I get until k gets to about n, then I can reconstruct. In the middle, I get this kind of exponential advantage. For the same two distributions, I didn't change the distributions at all. Okay? So sort of one thing to notice is that this is really sort of a peculiar phenomenon about symmetric distributions, right? It's very different from the kind of threshold behaviors we're used to seeing when you look at, linear algebra or things you do with things you usually do in crypto, where you cannot do k, but then you go to k plus 1, and then all the security breaks. Right here, it goes up like very, very slowly. Yes.
What alphabet clause means? What is k, comma k?
So this is the window. This is the number of parties that can look at the window at which you can look, and this is the advantage, the statistical advantage that you get. Yeah. So those good question.
So what do you mean by symmetric? Can you explain?
Symmetric means they're invariant under permutation. So it's a strong notion, right? When I permute all the bits, I get the same probability. Little k close means k0 close, yes. Yes, exactly. So this turns out to be tight, which is, well, it's not very surprising, but there are actually examples even for the n function where we can distinguish with disadvantage. And one other consequence is that you can look at all possible symmetric distinguishers. And this notion of approximate degree has been studied for them. We know exactly what it is. Well, I'm not going to explain to you what it is. I'm going to give you some examples. So for example, the approximate degree of the n function is square root of n. For majority, it's linear in n. And using this, you can design sort of secret sharing schemes with tight parameters for any, with respect to any symmetric reconstruction function for statistical distinguishing. Yes.
If you take like k-wise independent, like the classical polynomial-based, or even the example that you have with the 3 bits and the third bit is the linear combination of the two, then isn't it symmetric?
No, it's not symmetric. Why is it not symmetric? Okay, maybe that one is symmetric. I haven't thought about it. But if you look at sort of codes, then they're not symmetric. Right, if you look at, good, so yeah.
But then I go to the full, like 3 is the maximal length, and therefore it doesn't contradict the...
Yeah, 2 out of 3 you can do symmetric, but if you look at, say, I don't know, 4 out of 6, then there shouldn't be any examples of symmetric ones. Yeah, good point.
So just to make sure I understand, so you're saying that pretty much the thing that works for square root of n more or less works with very decent security up to n to
Yeah, automatically, yes.
So I see. So it's actually much higher than I see.
Yeah.
Did people know it, or I mean,
It's a new result, so yeah. Okay. Should I try to give a sense of the proof?
Yeah, you have
12
12 minutes.
minutes. Okay. Yeah, I wanted to show you. So this uses like kind of different methods, but again, it has this kind of nice connections to analysis. So I want to at least sort of give you some idea about what's going on. There are some nice problems going on. So how do we analyze this? And here, sort of the way we do it is, so how do you take advantage of the distribution is symmetric? The nice thing about symmetric distribution is that there are actually very few distinguishers that you have to worry about, right? So when you have general distributions, sort of basis of distinguishers means all point functions or all parity functions. But for symmetric distribution, all you have to handle are the Hamming weights. So this is sort of the kind of distinguishers that you have to worry about. It's a distinguisher that exactly tests if the Hamming weight of the input, or the part of the input that it sees, right? It only sees like these big k bits of the inputs, is exactly some number. Do I see only zeros? Do I see exactly 2 zeros and 4 ones? Right? Those are the kinds of distinguisher. There are not too many of them. There are only k plus 1 of them. So as long as I can handle any one of them and I can show that any one of these cannot distinguish, then I can handle everything. Right?
Sorry, I'm just curious in case you don't get it. Do you know the answer? So I'm just trying to see. So you're saying if you design a very good visual secret sharing
Yes.
Somehow up to like, I don't know, n to 100, it's kind of pretty much almost perfectly secure.
Yes.
For n, obviously you can reconstruct. So what kind of happens? Is there a sharp kind of jump?
So I don't know what happens around n. First of all, I should qualify this, that this works only up to n divided by some large constant. So maybe at n minus 1, there's some.
You don't know.
No, here, so, okay, so in the visual case, sort of what this formula tells you, there little k square root of n, right? So in the visual case, you kind of get what you need, because when this big K approaches n, then the security smoothly goes to the value it should. I mean, modulo this term here, which might not even be necessary. Yeah, it's a bit more interesting what happens for the majority function, I think, because there little k is n itself. So the security is n squared over n, right? So then sort of, you might get a jump like near the end. I don't know what happens, but this is this constraint over here. So very close to the end, I don't know exactly. It might be an interesting range of parameters to study. Any other questions? Okay, so these are the kinds of distinguishers that you want to look at. And it's a basis of distinguisher for symmetric distribution. So as long as you can handle this, you're good. So what does this distinguisher do? It picks any k bits of its choice. It doesn't matter which case, because it's a symmetric distribution. And it just counts, are there exactly W zeros among these k bits? Are there 2 zeros and 2 1s? And there are two things that are important about this. First of all, is because it only looks at k bits. It's a degree k polynomial over the real numbers. And the second thing is that if I feed it an input which has very small Hamming weight, so for example, something that is always 0, then it is sure to reject, right? It will never accept, because even if the window it looks at, it's not going to see any 1. So it's going to reject all strings that have very low Hamming weight, and it's also going to reject all strings that have very high Hamming weight. If I have something that has many, many, many 1s, then in this window that I'm looking, I'm always going to see something that has many, many 1s. So I'm going to reject, right? Think of W as being n over 2. And the main claim that is shown is that, well, the average version of this function, so the symmetrized version, whatever that means, is actually almost a low-degree polynomial. So again, it's a claim about polynomial approximation, is that I can write this function as a polynomial of degree little k plus some error term, which is uniformly bounded everywhere, right? And then if I can do this, then I'm done, because like the error can never be much, right? This polynomial cannot distinguish between these two distributions, and this error term is not large. So the statistical advantage it gets is going to be small. So the way that this is proved now is I'm kind of going to turn the tables, and instead of working over functions over bits, I'm going to go on the real line. I'm going to work over functions that take real inputs. The point is that when I average this function, if I look at only like some random window of big k bits, it's actually a symmetric function. And it only depends on the Hamming weight of the input. So it is a function of the Hamming weight of the whole input. Okay? And now if I look at this as a univariate polynomial of the Hamming weight of the input, it's also a degree k polynomial. And it's a degree k polynomial that evaluates to 0 when the input is a small integer, and it evaluates to 1 when the input is a large integer. So this pretty much specifies the polynomial uniquely. It's a degree k polynomial that evaluates to 0 at all these k points. So I know the factorization of the symmetrized version of this distinguisher. So I get some kind of algebraic formula that tells me exactly what is going on here. And now I want to show that this polynomial, I get this formula for it, can be approximated by something that has much, much lower degree. How do I do that? So let me sort of give you the impression of sort of how would I argue that a high degree polynomial can be approximated by a much, much lower degree polynomial. So here are the things that I tried before I knew how this is done. And then I'll tell you sort of what I learned and what works in this context. Well, the first thing you can try to do is you can try to approximate this polynomial by taking the lower order monomials, right? I take the monomials 1, t squared, t cubed, and so on. Okay? So when I do that, in particular, let me sort of think of the case when the number of parties goes to infinity. So this is something I should have mentioned. I forgot to say it. Sort of one other thing which is kind of very interesting about this bounce, I think, is that it doesn't depend on the number of parties at all. Sort of the bounce that you get on the statistical distinguishing is the same regardless of whether you share it between 1,000 or 1,000,000 parties. You get exactly the same bound. So if you have a large number of parties, then this polynomial looks very simple. Sort of this is what it looks like. If I draw it, scale to -1 and 1. So this is what happens when the distinguisher is just something that looks at the Hamming weight and it only accepts when it's 0. This is what it happens when it accepts, say, 4 out of 6, if I have four ones out of 6. So then it mostly accepts strings that have about 4/6 of the entries being 1. Right? And now the question is, how do I go about approximating this polynomial with something which has lower degree? Okay? I can try to do it in the monomial basis. This has a very simple formula. And if you write it down at the monomial basis, you get this kind of, like it's t-1 raised to the power n. So you get this kind of bell curve distribution. If I chunk a lot of the weight here is contained in the higher order terms. So you don't get a very good approximation. So I just want to sort of tell you, it's a bit impressionistic at this point, but I want to sort of tell you what I learned from this. And maybe a little bit about how it ties together. So if monomial basis doesn't work, sort of if expansion doesn't work, what am I going to try to do? Well, the next kind of basis I try to expand functions is in the Fourier basis. And sort of here is sort of where the struggle is when you try to expand a function like this in the Fourier basis, right? This is a real valued function. It takes real values between 1 and 1. So how do I do a Fourier expansion of this function? Well, to do Fourier analysis, I have to work over some groups. So I have to sort of make it periodic, wrap it around the circle. But if I take a function like this and I try to make it periodic, I get this odd discontinuity here. So you would expect that when I write down the Fourier transform, it will behave very weirdly around here, and I wouldn't get a good approximation, right? So what do you do? And it turns out that there is this trick that is really, really simple, and that comes from sort of signal processing and engineering that gets past this problem. Okay? It's like the most naive thing you could think of, and it works. So instead of applying the Fourier transform to this function, you take its mirror image, and you put it next to it. And now there are no discontinuities anymore. Okay? Now when I take a periodic function, it's continuous. Okay? And now if I take the Fourier transform of this function, it looks very nice. And this is what's called a cosine transform. So now sort of when you do the algebra, instead of it being a function of sort of over the complex circle, it's a function over real numbers. And the real number that you take is the cosine. You can write it as a cosine of some angle on the complex number. And you expand this function as a cosine series. So you take cosine theta, cosine 2 theta, and so on. And each one of these is a polynomial of this term. And these are exactly what are called the Chebyshev polynomials, right? Cosine 2 theta is a degree 2 polynomial in cosine theta, and so on. So they look like this. And then if you expand the function under this basis, then things work out for reasons that I don't have time to explain because I only have 2 minutes. But it turns out that if you want to analyze functions over the real numbers, this is the right basis to use because in some sense, it gives you the optimal approximation up to some factor that depends on the degree of the polynomial that you're approximating. So for the rest of it, what we do is we sort of develop these tools to analyze this Chebyshev transform. And you get these kinds of pictures that tell you what these Chebyshev coefficients look like. And you see that it's kind of like a bell curve, but not exactly. For some values of parameters, it can be a bit of a mess, and so on and so on. And well, in the end, you get what you want if you work hard enough. So I'm going to sort of not say anything about this. I just want to say one more thing, because I threw a lot at you, which is this whole thing works very well over bits, but I don't even know what happens when the alphabet size is 3. So this is sort of an open question. You have the 2 symmetric distributions over trits. They're locally perfectly indistinguishable on k bits. What happens when I have k plus 1 or 2k bits? Like, do I, again, get this kind of slow distinguishing advantage, or is it something very different? I don't know the answer.